second talk. So our second speaker is Professor Robert Hovden from the University of Michigan, Ann Arbor. Rob and Anna went to the same group at Cornell, so he's like a family member of mine, and I really want to thank him for the article he contributed to the focus issue. It reads like a breeze. I highly recommend everyone to read it. So Rob is assistant professor in the Department of Materials Science and Engineering at the University of Michigan. He received a BS from Georgia Tech and his PhD from Cornell. His research focused on the limits and three-dimensional imaging in electron microscopy to unveil how structure at the atomic scale and the nanoscale determines the microscale materials property. So today his talk is going to be about electron tomography for functional materials. Rob, the mic is yours now.
Okay, thank you. Thank you, MRS, for hosting these wonderful seminars as we cope with the pandemic lockdown. I think it's a great thing. The goal of this talk is to highlight the maturing field of electron tomography and its widening scientific applications that are utilizing 3D structure, chemical, and functional imaging at nanometer and subnanometer length scales. For nanoscale characterization, it's been a long-standing goal to observe and quantify three-dimensional structure. Not just surfaces, but the entire internal volume and its chemical arrangement. We've seen over the last 2 decades, electron tomography has progressed substantially, both in resolution and dose, as well as chemical sensitivity. Combined with recent innovations in computational resources, reconstruction algorithms, 3D visualization tools, scientists are now interactively dissecting volumetric representations of their specimens and extracting meaningful statistics of their three-dimensional structure. Remarkably, however, electron tomography predates the personal computer. In 1968, Rosier and Klug famously reconstructed the helical structure of a bacteriophage tail from a single TEM image using prior information about its helical symmetry. Prior information about spherical symmetry was used to reconstruct a negatively stained human wart virus, and electron tomography as we know it now was achieved in the mid-70s to reconstruct a low symmetry fatty acid molecule. In the last 2 years, we've seen exponential growth in the number of biological structures reported using electron tomography. And this exponential growth in biological systems has bled over into an exponential growth in electron tomography for material systems. And it's blossomed across many fields, such as semiconductors and clean energy nanocatalysts. Initially, the biological TEM techniques were applied to reconstruct polymer morphologies where similar contrast mechanisms could be employed. However, in 2000, TEM tomography of silver particles on zeolites opened up 3D characterization of inorganic matter. While biological specimens are radiation sensitive, many inorganics can withstand orders of magnitude higher beam dose, and this allows for wider characterization, use of wider characterization methods as well as higher resolution. So on the right-hand side, we see the dose requirements against resolution. We see that silicon dioxide, the horizontal dashed line, can withstand many orders more dose than typical organics. The lines labeled 40 or 80% represent the dose requirements of tomography at a given image contrast level. Since this is a log-log plot, we see that better resolution requires significantly higher doses. So with more dose, we can get higher resolution, but in addition to higher resolution, higher doses also allows us a wider range of imaging techniques. In particular, it was STEM tomography that was a marked innovation for characterizing functional nanomaterials in 3 dimensions. Midgley and colleagues, they utilized an ADF STEM detector to produce 3D reconstructions, where the value of each voxel in that 3D reconstruction was proportional to the proton density that comprises the material. It's a key feature of STEM that it provides simple projections that allow for quantifiable tomography. So on the right-hand side, I'm showing a cartoon of a scanning transmission electron microscope, STEM, where electrons are accelerated to 50 to 80% the speed of light, and they're focused onto the entrance surface of the sample using a series of electromagnetic lenses. The full width half max of that probe, that electron wave function, is just a few angstroms, and it's scanned, it's rastered across the entrance surface of the sample, and the highly elastic scattered electrons are collected in this annular dark field detector. That's a Rutherford scattering process, and it provides us a simple projection image of our specimen. So if there's one takeaway message, it's that STEM tomography has been a significant advancement for quantifiable 3D characterization. And so when we do a STEM tomography experiment, we collect projection images over a wide range of angles. And we do that by tilting the specimen relative to the beam. Typically, we'll tilt around plus or minus 70 degrees, and we'll take a projection image every 1 or 2 degrees. With a large enough number of projections over a wide enough angular range, we can then reconstruct a three-dimensional object. It's the Crowther criterion that describes the number of projections we need for our reconstruction. Each projection in real space maps to a plane of information in Fourier space. And it's the missing information between each plane that limits the resolution and the total size of an object we want to reconstruct. So the Crowther criterion states that if we want higher resolution, better resolution, and we want to reconstruct larger objects, we will need more projections. Nonetheless, with a sufficient number of projections, our two-dimensional images can come to life. We can get beautiful 3D reconstructions of our object. We can see, for example, here in these spongy copper platinum nanocatalysts, we see their distribution in space. We also see that qualitatively, we can see that there's a size distribution. But in addition to that, with tomography, we get the complete volumetric information. So we can isolate and slice through individual nanoparticles and reveal, in this case, internal pore structure. So nanoparticles have lent themselves well to electron tomography, and it's found a lot of applications in clean energy nanomaterials, where the performance is intimately connected to the complete 3D structure, whether it's nanocatalysts for water splitting, hydrogen fuel cells, or electrodes on a battery. The surfaces are often engineered to maximize surface area where the reactions occur, and these complex morphologies are difficult to discern from a single projection image. So tomography reveals the internal structure, as we saw in the pores of the copper platinum particles, or here it tells us the location of the platinum particles on a carbon support. So this is a fuel cell catalyst nanostructure where platinums are loaded onto this carbon support in 3 different systems. And what the tomography done by Elliott Paget and colleagues revealed is that the platinum particles can lie on the exterior or on the interior of these carbon supports. Here the platinum particles have been labeled red for those on the exterior or blue on the interior. And distinguishing their location either on the exterior or the interior is a luxury afforded only by electron tomography. It was electron tomography that then was able to correlate the overall bulk catalytic performance, in this case the utilization of platinum, and correlate that to the nanoscale structure of the material. Here finding that the utilization goes up as the platinum fraction on the exterior goes up. So this work also highlights another benefit of ADF STEM, which is that we can distinguish chemical elements, in this case platinum and carbon, when the 2 chemical species are markedly distinct. However, if we have complex chemistry, say silicon dioxide layers at a silicon interface, knowing the exact chemistry in 3 dimensions becomes very challenging. But STEM gives us additional signals beyond the ADF detector. So in addition to the elastically scattered electrons collected in that annular dark field detector, inelastic scattering events can produce chemical signatures which we can collect, either through X-ray emission, which new detectors with larger solid angles and multiple detectors that allow for high tilts that reduce shadowing is allowing us to do EDX, X-ray spectroscopy, in a tomographic geometry. In addition to that, we can sort the inelastically scattered electrons by their energy loss in an electron energy loss spectrometer, and we've seen hardware improvements that are allowing for better detection efficiency on EEL spectrometers. We're also seeing more usable beam currents, and in combination, these things are allowing us to do spectroscopic mapping, and we can do spectroscopic mapping across a range of tilts. So on the right-hand side, we're looking at a chemical map of platinum and cobalt taken from an EEL spectrum before and after cycling in a fuel cell. What we see is the platinum cobalt core shell particles can coalesce. So we go from A to, say, figure B, and in figure B we see 2 distinct cores that reflect the original 2 particles that existed before coalescence. So spectroscopic mapping is giving us chemical projections of specimens. And if we collect chemical projections over many projection angles, we can do chemical tomography. One demonstration of this here is shown for an iron-nickel nanoparticle, which the iron and nickel is relatively homogeneous. However, after in situ oxidation, we see that the system phase segregates into a nickel-rich region and an iron-rich region, and cavitation also occurs. This cavitation is driven by a Kirkendale effect, and we can see that the cavities can be single, hollow, large cavities, dual cavities, or porous cavities. The findings in this work showed that metal concentration, diffusivity, particle size are all important parameters that dictate the mechanical and phase stabilities of a hollow oxide shell. We also see the need for electron tomography in the semiconductor industry, which has specifically emphasized the need for 3D characterization of transistors, memory, and interconnects. And it's motivated by the technological shift to stack 3D architectures that contain feature sizes at or below 1 nanometer. It's a strategy to beat Moore's law, so the industry is leaving the confines of the two-dimensional planes in order to pack more devices into three-dimensional volumes. The work on the left shows a 28 nanometer PMOS high-K metal gate transistor where using energy dispersive X-ray tomography, so that is collecting the X-rays emitted when doing STEM tomography, they were able to map 7 elements in 3 dimensions in this device, including a copper interconnect, silicon dioxide layers around the gate, an active silicon region, and even the hafnium gate oxide layer, thin hafnium gate oxide layer in the material. On the right-hand side, showing how plasmon mapping using EELS and energy filtered TEM was used to map silicon nanoparticles inside a silica matrix. So this is a system where the contrast of these two materials would be difficult to reconstruct using traditional tomography techniques, but by using spectroscopic methods that map the plasmon resonances, they were able to reconstruct the 3D structure of these silicon nanoparticles inside a silica matrix. STEM tomography has also been used to identify local defects in vias of DRAM and stress void formation in tantalum-lined copper interconnects. So a copper interconnect is reconstructed on the left, and on the right you see a thickness profile that shows a pinhole defect in the liner thickness. So here we're seeing that the liner thins at a specific site, and it's highlighting that many of these defects occurring in semiconductors are localized in 3D space, and they can't be quantified, or they may be overlooked entirely if you try and perform failure analysis from a single projection image. So last, I want to emphasize that electron tomography is very much entrenched in data science. So after the experimental data is collected, there's an extensive data processing pipeline that leads to the final 3D visualization and analysis. And I'd love to highlight a lot of amazing research that's been coming out of tomography groups using new computational methods, but it's outside of the scope of and the time I have for today's meeting. But there's been wonderful advancements in reconstruction algorithms that are resulting in higher resolution and more dose efficiency. And I believe this is going to allow us to image a wider class of materials in 3 dimensions. And in general, tomography is not something that requires state-of-the-art instrumentation, especially if you don't want to do chemical tomography, which again is a very new and challenging area in development. But STEM tomography, many of the things I showed today really requires the right expertise and access to the right software tools. If you're interested in beginning tomography or you're already doing tomography, please check out tomeviz.org. It's a comprehensive open source tool that you can use right now. The animated 3D visualizations throughout this talk were made in tomeviz. So with that, I'll thank the organizers as well as the funding agencies, DOE and ARO. This talk was based on a review article I wrote with David Muller, and it's appeared in this month's issue of MRS, which Holin Zinn was the editor, and I thank him for the opportunity to contribute. And thank you for your time, and I'll take any questions.